Jens was a graduate student at MBA with Russian Senate, where he also postdoc, before coming for, I think, the best time of his career so far at CITA. And he left, obviously, in October to take a position at Johns Hopkins. So Jens is here, he's going to be talking to us today about CMB spectral distortions and more recent work.
Yeah, I'm really glad that I could come back, and I can definitely attest to the statements made by Richard about the best time of my life here, scientific life, definitely. So I'm going to talk about work which I have been doing over the past few years, and some of the work also was carried out here at CITA with folks, the collaborators on this here. I'm going to try to convince you that CMB spectral distortions are going to be really, really interesting in the future, and that you can learn a great deal about the early universe and early universe physics, particle physics, by looking at spectral distortions. So I wanted to show this all-sky map from the W map, from the Planck. It doesn't really matter, it's basically the same. But anyway, from the Planck all-sky map of the CMB temperature anisotropies. And usually I would be, showing a couple of slides, making propaganda why CMB anisotropies were so amazing, and we learned so many things about the universe, and we're in precision cosmology, we can ask questions about inflation, we can, there's all these things which you can fill, many talks about. And I don't have time to go into all this, but I, of course, wanted to emphasize that there was really, we have learned a great deal about our universe, and what are the constituents of our universe by looking at the statistics of these temperature anisotropies. But I'm going to not talk about these temperature anisotropies, so the spatial variations of the CMB temperature in different directions. I'm going to talk about the spectrum of the CMB, so the energy spectrum. I'm looking at deviations from the black body shape. And since Kobe-Firas, now some 20 years, 25 years ago, Kobe-Firas has shown us that the CMB spectrum is extremely close to a black body with temperature 2.7, 2.5, 2.6. If you look at the latest value, latest estimate from the old data, black body where the theoretical curve and the data are basically indistinguishable on this plot. You can't, there's very little space for any spectral distortions. And here, this is just characterized here by the mu and y parameter, which I will explain a bit more later. But it just, the bottom line is Kobe-Firas has shown that the CMB spectrum is really close to a black body with very little space for spectral distortions. And why would you actually expect any spectral distortions? If you take, if you're in the early universe, very, very early times, let's say redshift 10 to the 6, 10 to the 7, then the expansion of the universe is rather slow, and initially everything is in full thermodynamic equilibrium. So you are certainly, it's very, very easy to convince everybody that you will start with a black body spectrum. And if there's nothing especially happening, then just this expansion of the universe is not changing anything about it. So you will always, the CMB spectrum will always be just characterized by one number, which is the temperature, which scales like 1 plus z, just cooled as the universe expands diabatically. But if you have some process which perturbs this equilibrium, just think about a bomb going off in the universe. You inject some energy, or you create some photons, then you're perturbing this equilibrium, and you have to restore it. And this time between the energy release or some perturbation in the equilibrium between matter and radiation until the time when we observe it, that time determines how closely you can restore the full equilibrium. And just to give a very simple example, if you imagine you take a CMB black body, the CMB black body spectrum, and just shift all the photons up by some fractional energy, a very small amount, then you change the total energy density of the CMB. So the temperature, the effective temperature corresponding to that energy is slightly larger, but you didn't change the number of photons, I just shifted the photons, which means it cannot be described anymore, the spectrum cannot be described by one number anymore. So you have a distortion. That's just the obvious statement of why you should expect any distortion. And from Kobe-Firas, as I mentioned, there's really, really tight constraints on these distortions. That also means there's very tight constraints on any energy release in the early universe. Early universe meaning really, high redshifts, redshift 10 to the 6, 10 to the 5. I'm going to explain this in more detail as well. Okay, so why bother about this? I just told you Kobe-Firas has not seen any distortions, and first important thing is there are several physical mechanisms which happen in the early universe which should lead to some distortions. Okay, some of them are more speculative, and I won't be having time to talk about all of them in great detail. But for example, here, evaporation of primordial black holes, superconducting strings, they can in principle lead to energy release and could distort the spectrum. But there's also something which I will spend some amount of time on, dissipation of acoustic modes. You have the small scale acoustic modes, and they dissipate the energy that leads to energy release, and it should be happening. There's no way around, which means you have some expectation from measurements at CMB scales. You have some expectation on spectral distortions here. There's recombination, which I will mention in passing as well, and there could be decaying or annihilating particles, relic particles which are dynamically unimportant, or something which is just making up dark matter. Then there's also the low redshift universe, where you get energy release from formation of structures, supernova feedback, and just the heating of the medium during the reionization epoch and structure formation epoch. So these are processes which should happen in the universe, and they should lead to distortions. And the reason why they haven't been detected is because the distortions are smaller than what Kobe-Firos was able to do. But the good news is that there is, in principle, from the experimental point of view, a possibility to go beyond the Kobe-Firos limits by a factor of 1,000. So this is a proposal which was submitted in 2011 to NASA as a Explorer class mission. So not that expensive, just 200 million, but of course that's not the cash you have lying around. But the main goal of this PIXIE mission was to measure depolarization at large scales, but it also had an absolute measurement, or an absolute calibrator, so it would be able to measure the CMB spectrum. And as I said, here is again this numbers mu and y, which could be improved by a factor of 1,000. You can't read this. This is 10 to the minus 8, and this is 5 times 10 to the minus 8. The limits I mentioned were 10 to the minus 5 and 10 to the minus 4. So this is a factor of 1,000 improvement over Kobe-Firos. That means that brings you into the ballpark of measuring these previously mentioned processes. And recently, and that is something which is exciting me very much, there has been this white paper put out. It's actually an L-class mission for ESA, which was kind of proposed at the end of May, called PRISM. And PRISM is again having two science goals. It's going to map the CMB anisotropies in polarization, with the goal to measure, of course, the polarization, B-mode polarization at large scales, but also going down to really, really small scales. So it's really having a very, very precise measurement of the CMB anisotropies down to scales corresponding to arc minutes. And then there is a spectrometer on it, which is similar to PIXIE, but it has slightly higher sensitivity. It will actually go 1 order of magnitude better than PIXIE, according to the specifications which were worked out. And you can see here just a picture of an image of this. The telescope is here is off-axis. When it's spinning, it's just scanning the sky. And there's this spectrometer, which is kind of on-axis, which is just pointing in one direction. And then as the satellite processes it, slowly scans the sky. And of course, I already mentioned the science goals will be depolarization down to tensor to scalar ratio 5 times 10 to minus 4, which is a pretty impressive number. And then it will do SE cluster counts. Actually, all SE clusters promised all SE clusters at masses above 10 to the 14 solar masses, and galactic science. But for me, the CMB spectral distortions, average CMB spectrum, will be the interesting part. And this, of course, is very encouraging in terms of there is not only processes which should be there leading to distortions, but there is also the hope that you might be able to look at this. And to put this into perspective, here's the history of the universe, sketched by this is taken from the Planck folks, and we have here our inflation epoch, and then a lot of stuff happens, and we have here recombination, where we get the CMB anisotropies from, and we have formation of structures, galaxies and all these kind of things, reionization. This is just a standard picture, and when you're looking at the CMB anisotropies, you're trying to learn, for example, about inflation at much earlier, which are setting the initial conditions for the CMB anisotropies. If you look at the CMB spectrum, so the distortions, you can actually probe any energy release basically below something like a few times 10 to the 6 redshift, where the universe is basically a few months old. If energy release happens a few months after the Big Bang, any energy release will lead to some spectral distortions, which you see. And I will try to fill this, give a bit more detail about what's happening here in the talk. But there's a huge, it doesn't look that impressive here because the scale is, we're looking at. But there is actually a pre-recombinational epoch, which is not probed directly, which could be probed by the spectrum. And you have a large discovery space here. You can look at decaying particles, you can look at dissipation of acoustic modes, and these kind of things. I will try to explain a bit more. Okay, so how does thermalization work? Because we're going to talk about this a bit more, and I will give examples. But I think it's important to at least roughly understand how this works. So there's some conditions which I just want to briefly point out here. The universe is really, in principle, everything is very, very simple. The calculation, we're looking at average distortions. So we don't have all these details coming from, structures and so on. It's very, very simple. And in particular, it starts, before recombination, we just have a fully ionized plasma, helium with hydrogen, free electrons. Coulomb scattering makes sure that all the distribution functions for the electrons and protons and helium nuclei and so on are very close to Maxwell-Boltzmann. So you just have to specify the temperature of the medium, of the matter, and things are very simple, down to really low redshifts, redshifts of 10. I mentioned already the universe is homogeneous and isotropic on the largest scales, and that's all that matters for us here in terms of the average calculation of the average spectrum. And that makes the whole calculation extremely simple and very solid as well. You can really base your whole calculation on very simple physics. And you have the adiabatic expansion of the universe, where you, of course, have to worry about the fact that photons cool in a different way because of the adiabatic index than matter does. Okay, so that's just some background, words about the background, but there's also, I mentioned when you are injecting energy, you're changing the energy of the photons or the distribution of the photons. What do you have to do? Well, let's say there's a line, we introduce a line, then you have to make that line, you have to diffuse that line over the whole spectrum so that you can basically erase the signature of this line. That means you need something which is redistributing photons over frequency. And that's done by quantum scattering, which, this is a picture from one of Rashid's old papers, where you imagine you injected a line, and then because the plasma temperature is slightly more energetic than the line which was injected, you get an average upscattering of the photons. The line also broadens, but this is like, this is the standard Compton scattering physics which goes into this. You can describe this with the Companet's equation, which is giving you a picture of the repeated scattering in this uniform medium. And because this is one of the distortions which are really important, and I mentioned it already, the Y distortion, the low Compton Y parameter solution of this diffusion equation, where the Compton Y parameter is basically given by nothing else than the Thomson scattering efficiency or optical depth multiplied by the energy exchange rate. You basically can, with that parameter, you can describe how strongly are photons redistributed over frequency space. And the solution of this is also known in connection with the Sunyaev-Cerovich effect, where you just have, the CMB spectrum, and you shift all the photons by some amount upwards, and then get the characteristic distortion, which is called, Y-type distortion. Okay, I said, okay, this is now just diffusing photons over frequency, but that's not enough. You need to restore the number of photons as well. You need to change that. And for that, the first thing you pull out of your pocket is, of course, Bremsstrahlung, because you have, free electrons, they're flying around there, and you have the protons. You will just produce a Bremsstrahlung. But we're in a very, very photon-dominated universe. So the entropy of the universe, specific entropy, is dominated by photons. In that case, you're actually double quantum scattering, a process which is very similar to, if you look at this is the Bremsstrahlung process, where you basically have a radiative correction to the Coulomb scattering. You just create a photon. Similarly here to the Compton process, if you take this photon away, this is nothing else than the first order radiative correction to the Compton process, for those people who don't look at this every day. And this is the process which is most important at high redshifts. At redshifts above something like a few times 10 to the 5. So how does this work? If you're starting with basically no photons, but you have a hot plasma, then once you're producing some photons with Bremsstrahlung, you will immediately get you create an equilibrium at low frequencies because the photon production is very efficient at low frequencies. Then Compton scattering slowly moves those photons up and fills in the gaps at high frequencies, and more photon production will then at the end of the day will really thermalize the full situation. So you have this energy density in the electrons, and they get drained, they lose energy by photon production, and then scattering makes everything after a long time go through to an equilibrium, which is a black body distribution. Okay, so that's just the physical ingredients, but one can make this, look. This is now the kind of thing which I think should be, easy to understand how this all works. So imagine you put a set of a bomb at some redshifts. This is what I'm doing here, and I say I want to know what is the final frequency distribution of the non-black body part. That sounds almost that I'm always talking about distortions here, but when you do this, for example, at extremely high redshifts, a few times 10 to the 6 in our universe, then the spectrum which you get out of this, so you took away the black body ambient radiation field, and you are left with something which looks like this red curve. This is the response function for setting off a bomb or injecting energy at high redshifts. This is actually nothing else than shifting the black body to another black body. Because you are at high redshifts, you're fully thermalizing things, and all you do is, you shift this is the shape you need to correct a black body, which was, initially lower temperature to go to a higher temperature. So this is not a distortion. This is just shifting one black body to another black body because thermalization is so efficient. Until the time when we are looking at this, we see no difference. It's a black body again. Okay. If you do energy release at redshifts 3 times 10 to the 5, then you get this characteristic shape. Now this is really a distortion, and it's called the mu-type distortion, where you basically say there's a constant chemical potential at all frequencies. So the chemical potential 0 means it's a black body, and if the chemical potential is non-zero, you have this type of distortion for energy release at redshift around this. And the reason why you get a constant chemical potential is because a Bose-Einstein spectrum, so a constant chemical potential, is actually the solution of the Combinates equation, which describes the scattering of photons, the equilibrium solution in that case. So you're in this regime where you're scattering very efficiently, and you're driven towards a kinetic equilibrium with the scattering. Then you go to low redshifts, below 10 to the 4, you get this distortion. And this one is the one which I have already mentioned. It's the Y-type distortion, where you just partially upscattered and got a partial upscattering of the photons. Because the electrons are slightly hotter, you get this SC-type, high redshift SC-type curve. So these are the 3 cases, but there's all the intermediate cases. And these intermediate cases are actually telling you something about the time dependence of when things happen. And that's a really important aspect which has been completely not used in previous studies. There was always just, there's a temperature, there's a mu distortion and a Y distortion. These don't tell you anything about when things happened. They tell you roughly, okay, if it is a temperature shift, you wouldn't be able to learn anything, by the way, because you don't know what's the reference temperature. If there's a temperature shift, I had to inject energy at redshifts above 10 to the 6. If there's a Y distortion, I had to inject energy somewhere at redshift below 10 to the 4. So, and if there's a mu-type distortion, it must be somewhere in the redshift regime, a few 100,000. But there's all these intermediate cases, and you can learn about the time dependence. And you will probably ask the superposition.
No. It's actually just simpler. So the reason you have a mu-type distortion is because you're conserving photon number, and that's just so the difference is mostly whether you have lots of extra photons around there getting upscattered or not.
Yes,
that's the main.
It's correct. So this is not so low frequencies. I should have pointed out, of course, as well. This is really observing frequency for us. This is low redshift observing frequency. So So we're talking about 100 gigahertz, terahertz, and 30 gigahertz. Photon production, even in the part where you get full thermalization, is always important at much lower frequencies. So you would see all these curves deviate at low frequencies, and especially if you look at number of photons, because the photon production is pumping into low frequencies, and then the scattering physics is just transporting them upwards. But at high frequencies, zero photon production, or very little. That means your distortion is really characterized by a constant chemical potential, or this, Y. Yeah. So,
but this is the amount of photons you have at high energy is just a function of time. Is that why you get different variations from this constant case as you go?
Yes, that is correct. Yeah, but one might want to say that this is still encoding as well the efficiency of scattering in this case. The reason why you're driven from here to here is because you're kind of getting, here's the regime of extremely efficient scattering, here's the regime of inefficient scattering. And then you're driven between these two extremes because of the efficiency of scattering. You can say if the Y parameter is extremely small, it's -2, you're in this regime. If it's extremely large, 1,000, you're here. And if you're like at 1, you're in between.
I thought you said just now that both the mu and Y distortions conserve number of photons, but you've been talking a lot about creating photons.
Yeah. So the story is that when you're out of equilibrium, the first thing that happens to the spectrum is you create, because you're at very short time afterwards, you're in the Y distortion limit. You just make the electrons slightly hotter, and you would have a distortion which looks like this after an extremely short time. Then time goes by. This one decays to a mu distortion because you're evolving, and the reason why you're evolving there is just because you wipe out the distortion of a frequency. And then photon production is produced photons are produced at low frequencies. They get transported slowly to high frequencies and diminish this blue curve basically. And once you're diminishing this blue curve, you're starting to decay to this red curve. So it's a combined action of first I redistribute only, and then I actually fill in the gap by producing photons at low frequencies. And the red curve is the fully thermalized spectrum, which needed photon production. Yeah, this one is not conserving photons. This one is actually adding photons. Okay, so this is the slide which I already had, and I showed you. There's this post-recombination, pre-recombination epoch. Let's fill this in here. This is just rough. I didn't do this very carefully, but it's roughly like this. At redshift 10 to the 4, everything gets below 10 to the 4. You get a Y distortion. This one extreme. In this era here, between 10 to the 4 and 3 times 10 to the 5, you get a mu-Y mixture, but also some residual. It's not just a pure superposition of these two extremes, but there is a residual. I will show this in some examples. And then there's the era where you get dominantly a mu distortion, and then at very early times, at a few times 10 to the 6, above that, you get just a temperature shift, which will not tell you anything about the universe unless you have a way to measure the temperature here, and then measure the temperature later. And for example, BBN, you can use that, but that puts you a constraint which is rather uninteresting compared to the constraints which we are talking about, like a few times 10 to the -5. There's no way to really learn something about the monopole from the monopole temperature. Okay, so let's go back to this list here, and start with talking about this one. So the energy release coming from structural formation and heating by stars and all these things. Here's the spectral distortion. Now everybody will be like, I don't know what this means, but the important thing is I plotted here because I'm going to show many orders of magnitudes. I plotted the logarithmic on logarithmic scales, the modulus of the distortion. So this is how a Y-type distortion, the Sunyaev-Selevich curve, how that looks in this particular way of plotting it. So here's the positive part, this is the thick line, here's the negative part. And that's a Y distortion of, I think, 5 times 10 to the -7. The medium during reionization is something like 10,000 Kelvin, maybe 20,000. Optical depth from WMAP, we know it's 10%. You get from that, you get a Y distortion of 2 times 10 to the -7. But there's also all this heating coming from, you know, shocks and supernova and all this. You can basically go in some regime between, you know, it's expected to be even close to 10 to minus 6. But I just wanted to show this as a, you know, guideline. So this is a Y-type distortion, and this is the PIXIE sensitivity. So you can see, you will measure with very high precision. This will be a, you know, 100 sigma detection of this distortion. And what does it tell you? That average signal, it kind of just tells you about how much is the average, what is the average temperature of the medium, how much energy release did you get per volume from the, you know, ionization. There is also the anisotropic signal from the warm hot intergalactic medium. I don't have time to talk about that, but in principle, because this is a 100 sigma detection, I mean, you could potentially at large scale see some anisotropics. And there's also, I mean, Planck has just, you know, shown this all-sky wire map, and you know, at large scales there should be contributions from this warm hot intergalactic medium. Okay, here another example. Here's a decaying particle with 114 years lifetime. I just tuned the parameters in such a way that the total energy release is something like, it was 6 times 10 to minus 7 delta rho over rho. So relative to the energy density of the CMB photons, a very small amount of energy release. But you get a distortion which, again, you know, in this case, you see it, which should be detectable rather well. You know, it's many sigmas above the detection limit. And the interesting thing, of course, this is a, you know, potentially a probe of, you know, particle physics at redshifts 10 to the 5, 10 to the 4. The interesting thing is that you can actually distinguish the lifetime of particles. I want to show this in detail now, or a bit more detail. So here's, as a function of redshift, the energy release rate. So I scaled it here. It's nothing else than the heating per CMB photon energy density as a function of redshift multiplied by 1%. This 1% factor is just coming from to make convenient scaling for the dissipation of acoustic modes. I will explain that later. But the shape of the energy release for a decaying particle is just looking like this, you know, power law with an exponential cutoff, because you're disappearing, you're really exponentially decaying, and it's gone. And this is the kind of type of energy release that you would get from a decaying particle. Here with a, you know, an equivalent a redshift, you know, the redshift. I just varied the redshift, which is, you know, the lifetime of the particle. This is a shorter lifetime, longer, and even longer lifetime. You see, you can have these, you know, different epochs at which you have the dominant energy release. And then you can calculate the distortion from that, and you can see that the distortion has, you know, the shifting from low to from the mu type distortion to the Y type distortion. And just for comparison here, you know, a Y type distortion of 10 to minus 7, few times 10 to minus 7, and you can see that this is in principle encoding directly the lifetime of a particle. But what is important is not that you're tuning between, you know, a mu and a Y type distortion. What is important that you're actually deviating from just a simple superposition of mu and Y. If you take so and so much of mu and so much of Y, then of course you can tune between the two extremes. But you can actually calculate that there is a residual. And this residual is not, you know, this is, here we're looking at a scale of a few hundred, yeah? And here we're looking at a scale of a few 10, which means we're talking about 10% effects. But the signal is now clearly depending on what is the lifetime of the particle. So if you have a high precision measurement, you can actually measure directly the particle lifetime. Or in other words, if you have a lot of energy release and you're like 100 sigma above your detection limit, you can probably see a 10 sigma effect in the lifetime.
So it goes up to the best fit to Y and mu?
Yes, that's right. Here I just took out mu and Y as the best fit of them, and that's the residual, which you will not be able to explain. And you can do a calculation of 1 sigma detection limits for these particles. Here I now have really the lifetime, so in seconds. Here's the redshift, which it corresponds to. So what we were talking about before, where you know, 50,000, for example, is something like a few times 10 to the 9 seconds lifetime of particle. I actually forgot to tell you what this means. This is nothing else than how much energy was released by the particle. So, but what is the normalization of this energy release curve. You know, I just set here this energy release, total energy release. This one was, I believe, 6 times 10 to minus 6. 10 to minus 7. I just set it to some number, and if you just tune the particle lifetime, the normalization is always the same, and you're just tuning the redshift at which you're depositing most of the energy. And you can also see this here, because the energy release this corresponds to, if you have 1 EV for this variable, you're basically talking about 6 times 10 to minus 7 for the total energy release. And here is the 1 sigma detection limit. Just seeing that there is a mu-type distortion, and this means that at redshifts, around 50,000 or a few 100,000, you can actually, detect energy release at the level of 10 to minus 8 in terms of the redshift, in terms of the CMB black body. That's a really, really small energy release, and you would be able to see the trace of this particles there. And for comparison, just to excite everybody, really. This is what the people who are doing, all these long constraints on long-lived particles from BBN or from light element abundances. This is what they would be getting from their estimates. They would see, this is from the free helium to the deuterium ratio. They would be, ruling out particles in this regime at a few times 10 to minus 1, and here in this regime for the long-lived particles, you really are having, you're basically a factor of 100 better than those guys with a PIXIE type experiment. And the blue dashed curve and all these others, which I don't have time to really explain, mu1, mu2, mu3, those are actually characterizing the residual distortion. We are working on a paper on that, about that now. But what you can see is that in this regime, you would even see a detection of this residual distortion with rather high significance, and that means you can measure the lifetime of the particle in this regime at a few times 10 to the 9 seconds to a few times 10 to the 10 seconds. This is just demonstrating this. Here is a forecast for the error with a 5 times PIXIE. That's basically something like the prism, even a bit worse than the prism. You would get 1% error on the lifetime of the particle in a redshift regime around 50,000. That's just because in this regime you actually have the largest residual distortion, and you will be able to probe the lifetime. Okay, so dissipation of acoustic modes. This is very interesting because it's actually providing a probe of inflation, and everything which is going in the direction of bipolarization, and you want to measure bipolarization a bit more, you're basically trying to get one number, which is the tensor to scalar ratio, and thereby constrain inflationary models. You can constrain inflationary models also by looking at the CMB spectrum of CMB average CMB spectrum. And how this works, I want to explain here now. So here's the CMB anisotropies. This is now WMAP 9, and here's just one of the previous, power spectra, which people have derived here from the SPT in combination with WMAP, and you see we have a great measurement of the damping tail. We know now up to L of 2,000, 3,000. We know very well how the CMB anisotropies are damping away. If you had a way to take away this damping effect, meaning the damping coming from silk damping, from the photon diffusion, you would actually have more power. You would, there's the intrinsic power spectrum. If you start with scale invariant, you would see some oscillations on top, but you would in principle have much more power you should see. But this damping took away that power, and that is equivalent to energy release. And how that works, one can explain very, very simply by thinking about superposition of black bodies. But what you can immediately realize from this picture, if you have a power spectrum which has a larger amplitude at small scales, I'm talking about scales much smaller than the CMB scales. I'm talking about scales of 50 inverse megaparsecs, 10,000 inverse megaparsecs. If the amplitude at small scales is much larger, you get much more damping or much more energy release. So you get a larger distortion. If the shape, if you have a curvature in the power spectrum, that also determines that means that you will get different energy release, and that means that you're depending directly on the amplitude and shape of the power spectrum. You're depending as well on the dissipation scale, which has some dependencies on the background cosmology, but that is not so important. There's also some not so trivial dependencies. You can probe, in principle, small-scale non-localities in this way, because if you have very, very squeezed limit non-locality, where the large-scale modes, which we see in the temperature anisotropies, if these are correlating with the small-scale modes and enhancing, the power at small scales, then you should see anisotropic mu distortions, anisotropic energy release, and you will see this correlation in principle. That allows you to probe small-scale non-locality in the very squeezed limit. I don't have time to go into this. There's also dependence on whether it's as a curvature or adiabatic modes, and the neutrinos themselves carry away some energy. But overall, what this is meant to say is the CMB spectral distortions allow you to probe, early universe physics. What is, what the inflationary, it's a direct inflationary probe. And it's another number, or actually a set of numbers you can put on the small-scale power spectrum, which then constrains inflationary models, which is really interesting. So how does this work? I wanted to just walk through this briefly. If you imagine you have a black body of a temperature T0, this is the spectrum, so intensity as a function of frequency, and now you just compare this to a black body with a slightly higher temperature and a slightly lower temperature. If you take the average of these two curves, the red and the blue, you don't get a black body of the average temperature. I set things up in such a way that that one had just a slightly higher and a slightly lower temperature. The average temperature was actually the one which T0, and only at low frequencies you see that it's kind of coinciding with the black body, but at high frequencies there's this mean tail excess. And that is actually something which is equivalent to Y-type distortion. So it doesn't matter, the equations are not important here. It just means that you can describe this average distortion by some black body part and a distortion part. And that distortion part is then what is basically creating the energy release, because you have photons in a box, and you're mixing them up by mixing these black bodies with Thomson scattering. One can do this, really do the estimate of what the distortion is by thinking about it in this way. You really, really, really just think. There's the photons, they have slightly different temperatures around you, and you have a very efficient way to mix them, namely the Thomson scattering. We're talking about high redshifts, where you have basically all electrons are free, and they're just mixing these black bodies. And when you take the energy density of some spatially varying black body, and just calculate what's the average over that box, you can see that you get a term which is 6 times the temperature perturbation squared. So in second order of perturbation theory, you get a contribution to the energy density, which then leads to energy release. You can calculate the energy release just by taking the time derivative of this part, and you get this expression, which you can calculate from the exact shape of the power spectrum at small scales. And the interesting thing is that the local monopole drops out of this problem, because electrons which are seeing the average, locally averaged monopole, they are of course always in equilibrium with that monopole, and they don't do anything to the spectrum because they are not scattering, they are redistributing only relative to the local monopole. The dominant term is coming from the quadrupole anisotropy, because if you calculate this average and really carry out all the transfer physics of what is happening with the anisotropies, then the main thing is coming from the quadrupole, which is if you look in Stephen Weinberg's book, that's like the shear viscosity term, which is just describing how you average black bodies. Okay, so this is just showing how the energy release history will look for different power spectra. It's just the standard power spectra. If you're not familiar with it, it's not that dramatic and important. All that it means is that when you have the amplitude of the power spectrum, you have the spectral index and S, and the running of the spectral index, you can actually plug that into the formalism which describes what the heating rate is as a function of redshift. And if I would have a scale invariant power spectrum, so in S equal 1, then the heating rate in this coordinate, so multiplied by 1 plus Z, would be constant. That's the reason why I had this 1 plus Z factor there. And you can see, this is for the WMAP 7 case, this is how the heating rate looks as a function of time, redshift. And you have energy release here in the mu era, you have energy release in the Y era, and here's just the mark. It's just showing where recombination is happening, because where recombination is happening, things are becoming a bit more complicated. It's not just all determined by the quadrant pole, but also higher anisotropies are important and so on and so forth.
Why do you use an NS that's ruled out by Planck?
Because this was an old slide, and I'm going to show you the new one as well. But it's not very different in fact. One thing I really want to emphasize, the modes we're talking about, so those guys were, the modes which are really leading to energy release in this redshift regime, those modes are really small scale modes. So this is from a paper which Adrian and Ido and I wrote, where we just said, okay, let's put a spike in the power spectrum, and let's ask what's the time dependence, what is the heating rate as a function of redshift. And first of all, you can see this is a spike at 200 inverse megaparsecs, so really small. You see that this is not just a spike in the energy release, it's actually a broad, oscillatory energy release, which has an average, which is, this is just cosine square amplitudes. And you see that the maximum is, this is just a simple expression showing you that if you have 10 inverse, 1,000 inverse megaparsecs, you will get energy release at 5 times 10 to the 5. So those modes which are leading to energy release in the mu era are actually modes which correspond to 50 inverse megaparsecs to 10,000 inverse megaparsecs, while modes which are leading to energy release at lower redshifts are below 50,000, below 50 inverse megaparsecs. So we're talking about really, really small scale modes which are not probed by CMB anisotropies. And here's the standard silk damping case, the spectral distortion you would get. Remember, here's the positive part, and here's the negative part. And you can see, for the standard spectral power spectrum, you would actually, be only close to the detection limit in the PIXIE with the PIXIE type setting. And this one was even slightly more optimistic because it was actually assuming a scale invariant power spectrum. And for that, you get a 2.5 sigma detection with PIXIE. So that sounds sad, right? Because there's no way actually to learn something great here, you would say, if you just extrapolate from large scales. But that is not the whole story. This is showing you what are the current constraints on the power spectrum, curvature power spectrum, from CMB scales. So this is below 3 inverse megaparsecs, 3, down to 10 to the 3 inverse megaparsecs. And you can see, okay, here everything is really, really nailed very well. It's, a few times 10 to the minus 9, that's the amplitude there, and you have very little freedom there. But if you go to smaller scales, corresponding to larger k, so 3 inverse megaparsecs and above, you see, at very small scales, everything is, possible. But even here, we're, in this regime, and I told you that I'm interested in regime up to 10 to the 4 inverse megaparsecs, you have a lot of freedom still. These bounds here are from ultra-compact mini-halos, which is basically, you look at the gamma ray background, and you kind of, by thinking about these ultra-compact mini-halos and their formation, you can estimate how much power you should have on those scales, just from annihilation. These are rather, with Adrian, she was explaining me many times that these are still, rather model dependent, but even then, we're talking about amplitude of 10 to the 6, 10 to minus 6, 10 to minus 7. So in comparison to 10 to minus 9, we have 3 orders of magnitudes, or at least a factor of 100 wiggle space there. And CMB spectral distortions will probe in this regime. And rather, they will probe very directly. So you can, if there is power, which is here, which is just, you have more power at these small scales, you will measure you will directly constrain this with CMB spectral distortions.
What do you get from Kobe-Farahs?
Kobe-Farahs would be somewhere here. We estimated that as well. So I'm just making something up here. So here's now where Lee will also be happy. Here's the spectral index. Here's the case Planck without running. This would be the energy release as a function of redshift. Here I also now have this intermediate epoch indicated. This is the one with running, 2 times minus 0.02. And here I just made up a case where I said there's a step in the power spectrum at small scales at some 30 inverse megaparsecs. And I'm not an expert on all these inflation models or whatever. I'm just trusting Adrian in this sense there. she told me that there's lots of models you can basically cook up, and you can make, as long as there's no real constraint, you can cook up some model which will do something. So a measurement of the CMB spectrum is basically allowing you to rule out all those kind of models. And if you have a flaring of the power, you get an energy release rate which looks like this, and you can calculate, of course, the spectral distortion, and the only point you should take away is they are all different. You can actually distinguish them by measuring the spectrum. That's the really important aspect here. And this is just showing you if you have a step in the power spectrum, which is roughly 10 times the amplitude of the power spectrum at large scales, you would see this above the PIXIE detection limit, and you would be able to measure this directly. This is just stating that you will be able to probe the small scale power spectrum in this way. This is just some constraints. I want to show this figure, which again it's basically asking nothing else than in the case of the decaying particles. You ask the question, for a given spectral index, what amplitude at 45 inverse megaparsecs would you need in order to have a 1 sigma detection in case of mu? And the black line is the mu detection limit. So you see, if you have 10 to minus 9 at that scale, you would get a 1 sigma detection of the energy release corresponding to this. And if you change the running, it's really nothing else than parameterizing the small scale power spectrum with a different pivot scale. For those who would like the details, you can see that you change these detection limits. And mu1, mu2, mu3 are describing now the additional information. It's the residual distortion, which is beyond mu and y. And you can see that if you're going at level 10 to minus 8 in this amplitude, you already would be seeing 2 numbers, which means you could constrain 2 parameters of the small scale power spectrum independently. If you're looking at this amplitude, you would be able to go 3. That means you can in principle get all the parameters of the spectral of the small scale power spectrum in this way. This is for PIXIE sensitivity. If you go 10 times deeper, if you're 10 times more sensitive, these detection limits go 10 times lower. You will probe 10 times deeper.
So you're saying that with only like 1 mu, basically you're not insensitive to like the explicit forms of the
Energy.
So it's basically all about the integrated value of the extra power in small scale, right?
Yes, exactly. It's not only that. If you just have mu distortion as a number, that is really just the total energy release, and you have having no handle on when it happened, except for some rough handle that it was high redshifts. But now we're talking about extra information, which I call here mu1, mu2, mu3. These are actually describing the real time-dependent information you get.
What is it actually? The difference between the different mu's?
So if you take the spectrum coming from a particular energy release history and you project it onto a mu and y type distortion, then you have a residual left. It's not just mu and y, and that residual has a time-dependent information, which is characterized by mu1, mu2, mu3. I don't have time to go into more details, but I would be happy to explain that. All that this means is when you have large amplitude at small scales, you will be able to measure the shape precisely. Or if you go deeper, you will be also able to measure the shape. At least you can constrain partially break the degeneracies, which is a really powerful tool to constrain the small scale power spectrum. Okay, if I'm too long, where am I? I can't see it.
You've got a few minutes.
Okay, good. So recombination radiation, you guys have seen this many times. I made it very short here. So we know that at redshift 1000 we have the recombination of hydrogen and helium. That leads to emission of photons. Just because you capture the electrons into bound states, you should release an energy. And this energy, which is released in form of resonant lines, this cannot get thermalized, so you really should see a spectral distortion at low redshifts. This is the observed. This would be the observed spectral distortion from the hydrogen and helium recombination epoch. Just here, intensity, also really the distortion as a function of frequency we would see today. You can see here the 2 cases I show is just hydrogen only, and then the case with helium. And you can see there's the Lyman alpha line, there's the Paschen alpha line bracket, and you see all these higher Lyman, these higher alpha transitions. And helium, the presence of helium introduces some features into the spectrum, which are characteristic of, they are actually at some characteristic frequencies, and they are, if there were no helium, course, there's also extra photons produced, and you get some interesting effects at low frequencies. This is, of course, a distortion which, it's not difficult to imagine that you could do cosmology with this, measuring the spectrum. You would be able to measure the helium abundance, the number of baryons, all these things. That is a clear thing. You can, it's just the dependencies of the spectrum on these parameters is pretty obvious. This is just demonstrated in this, but the important aspect which I really wanted to emphasize is that these lines, they come from different epochs. And I also mentioned that many times in previous talks. The hydrogen recombination lines, they come from redshift 1400, which is even slightly earlier than the CMB anisotropies, which are created in the last scattering surface, which has its maximum at redshift 1100. So if you're looking at the CMB anisotropies, you're kind of probing the universe at the stages of 380,000 years after the Big Bang. If you look at the hydrogen recombination lines, you would be probing the universe at 100,000 years earlier. If you look at the helium, neutral helium lines, you would probe it even earlier, another 100,000. And the doubly ionized helium lines are coming from redshift 6,000, corresponding to the 18,000 years after the Big Bang. So this is all in the sunlight case, and you can imagine that if there's something special happening between these epochs, you in principle are able to probe the thermal history precisely by looking at the reaction of these lines, how they are actually looking afterwards. To put this into perspective, this is where the recombination lines are. This is where PIXIE sensitivity is. If you take the total integral, these are like 65 channels, and if you just average all these channels, hoping that this is really going like root n, the error, you could probably get a few sigma detection of the average photons there, but that's not giving you, of course, any real cosmology or whatever. This would put just a proof of concept that they are there. Factor of 10 at least would be needed, and this is where the prism sensitivities are. So you would at least, you have a hope to detect the Paschen alpha and bracket alpha line. No, I'm wrong. This is Balmer alpha and Paschen alpha line, which is already interesting. You could really say there is these recombination lines. Doing real cosmology with this is, of course, that is a step farther away. But at least the prism sensitivity, which seems to be feasible, would be probing directly these recombination lines, which of course is really interesting. And I think that's where I will stop my talk, finish my talk. The CMB spectrum, as such, is really opening a new window to the early universe. You can do particle physics, learn about decaying particles. I didn't speak about annihilating particles, but in principle you can also probe those processes. You can look at the dissipation of acoustic modes and probe the small-scale power spectrum, and thereby really learn something about inflationary epoch or whatever early universe model you can come up with, and you can constrain it in that way. The predictions can be made very, very, this is very simple physics in the sense of the thermalization calculations. Really precise calculations are possible in principle. And what is really interesting, and the point which one should really make, nobody knows what the tensor to scalar ratio is. So if you spend money to look for the B modes at large scales, you might at the end of the day find there is an upper limit, but you will not necessarily have the detection of these B modes. You don't know. There is, however, processes in the early universe which should lead to a distortion which is the level of the distortion is known. And I didn't mention one of the processes which definitely leads to a distortion, which should be of the order of which should be detectable with prism, and the recombination lines, which I mentioned, should be detectable with prism. Those are two examples which definitely should be there. The small-scale power spectrum, if you just extrapolate from large scales, you should also detect something with prism. I think this is, a very interesting future in principle, future direction of CMB science and cosmology. So, and we can stop there. Thanks.
Question again?
Some neutrinos take away energy, but is it okay to understand those effects as like some sort of a minus mu or a minus y distortion?
No. So the neutrinos, they carry, because when you have the perturbations in the early universe and your photon transfer function, set up by curvature perturbations is partially immediately setting up some perturbations in neutrinos. And those neutrinos only weakly interact by gravity. And this is meaning that the unity perturbation in curvature does not give unity perturbation in photons, but it has a small efficiency factor there. And that's the reason why you depend on the neutrinos in this process. There is no real there could be some, if there were no perturbations in the photons, maybe gravity could be draining some of the energy into the neutrinos. But no, I don't think there will be a negative chemical potential. But you can get a negative chemical potential by the fact that the matter and radiation are not having the same adiabatic index. The matter is continuously draining some energy from the photon field, and the photons, by Compton scattering, are just heating them up all the time. That means they lose energy, and you get a negative chemical potential from that. That's the distortion which is definitely there, and I haven't mentioned.
So with something like PIXIE or Prism, you're measuring the spectrum, you're extracting of order like 4 or 5 numbers from it with y, mu, mu1, mu2, and but as you described, there's a whole like range of different effects that you're going to be able to measure. And particularly you mentioned like reionization could give you some very large signal. How much do you think you can disentangle? How many effects can you actually disentangle from such a small amount of numbers, especially with one very large one?
Yeah. The Y distortion itself is not a big deal. Some of the estimates which I did here, let me put this one here. Where is it? Dock is too long. There. This one is for one decaying particle scenario where I did put in a large Y distortion as a foreground.
Yeah.
And I put in freedom in the monopole temperature.
Right.
So I estimated the monopole temperature, the Y distortion, and then I estimated directly what is the amount of this decaying particle and what is the lifetime of the particle.
Yeah.
And this is for PIXIE values. And you can see, here you get, pretty 1%, 5% level constraints on these parameters. That's not a big deal.
So how would you mean you know Y reionization, which is another way?
No, it's not known. I just put in a model there. I just said, let me put in a model for the decaying particle, let me put in a model parameter for reionization, let me put in it's just, I could have made 10 to minus 6 here, or 10 to minus 5. I mean, it's just, I made it up. I don't know the number, but I can then recover it, given the noise in the spectrum. So this is a demonstration that in principle is possible. There's of course all these foregrounds as well, from dust and all these things.
Could you, can you imagine a way? I mean, I'm estimating you use like 3 or 4 numbers in this. Is there a way of disentangling
Yes.
decaying particle from
Yes.
energy injection by the small scale power spectrum?
Yeah. I didn't have a chance to really show this, but in the paper which we are now preparing, we can really explicitly do parameter model comparisons by looking at these numbers mu1, mu2, and so on. You can see this is a decaying particle energy release history, right? It's like it has a maximum, it's peaked, it has a width. Dissipation of acoustic modes. If you say there's a power law spectral index, and maybe some running, but not too much running, then this will always be something like a curved line here, right? So the mixture of mu, y, and the intermediate, if you put the line like this, is very different from what you have when you have quasi-delta function injection at different redshifts. Which means, assuming that the power spectrum is not too crazy, because of course you can also make up models where you have particle production, for example, Barnaby is one of the fans of this. You can have particle production during inflationary or reheating, and in that way introduce a bump into the power spectrum. That bump would probably be very degenerate with the decaying particle scenario of a particular lifetime.
Right.
So let's put it this way: you can, in a model-dependent way, or with some prior assumptions, you can certainly disentangle energy release coming from dissipation of acoustic modes in this way from a decaying particle, but in a generic way, no.
Right. I mean, there must be some level you're in 5 numbers to play with.
Correct. Yeah. Correct. But you can, as I said, assuming simplicity in the model, you can disentangle these.
So we kept saying PIXIE or Prism. Is there anything that
PIXIE can,
Or is Prism the super?
so Prism would certainly be great, but Prism is also 10, 15 years away. Whereas PIXIE, if it would get funded and it's much cheaper, Prism, the numbers were there, it's basically 900 million euros, which is, huge. PIXIE would be $200 million, which, is much cheaper. But of course, the current funding situation is not, any of those things are having a hard time to get funded. But there is another chance to propose PIXIE again, repropose in 2-3 years from now. Another basically Explorer class mission call from NASA. And if PIXIE gets selected, then PIXIE could rule out a lot of the parameter space already, and would be basically, this is a factor of 1,000 better than Kobe-Firis. It's amazing what you can, all the kind of constraints you can get on models, on different models are really interesting. And even PIXIE would return with some distortion, because it will definitely see the Y distortion from realization with very high precision. So, last question.
You sort of answered it. I was just wondering what the timeline was for PIXIE and Prism and the likelihood of them actually happening.
Yeah, who knows? But yeah, as I said, it can be. So if it gets funded, Kogu tells me that it can be flying and basically having data in 4 to 5 years.
PIXIE.
Yeah. Yeah. So that means it would be still at a time scale 2 times faster than Prism.
Are there other science cases for PIXIE, or are you and your colleagues maybe?
So the weakest point of PIXIE is that it's having very tailored angular resolution. So the angular resolution and sensitivity is tailored to measure the large-scale B modes, basically to the point where the lensing starts to be, the E-mode lensing, the B-mode lensing signal from E-modes is starting to get really dominant. So that's just, L of 100 or something. And that is of course, tailored very well towards getting B polarization measurements, which is exciting and hard to do from the ground at those scales, of course, harder. But it also means that you're assuming that you can, the small scale, all the small scale stuff, that you can actually handle all the foregrounds and so on. That's one strong point about Prism. You go to really high resolution, and then you can actually have a really highly spatially, resolved map of all the polarized stuff, and you can probably deal with foregrounds or with, all the contaminations at large scales in a much more clean way. So the science case for PIXIE is basically really going after the large-scale B modes to get the tensor to scalar ratio and the spectral distortions, which is, really both of them are really, really strong points. But Prism will definitely basically cover all the possibilities in that direction. We'll do amazing galactic science and cluster science and things. So it has a even more rich science case. But it's also much more expensive.
Okay, great. Thanks for coming, everyone. We'll be taking Yen's